In this video, we're going to learn how to solve linear differential equations. We'll start by learning what a first-order linear differential equation looks like and how to write it in standard form. We'll then go over the step-by-step process for solving linear differential equations using an integrating factor and work through several examples so that you can recognize when an equation is a first-order linear equation and then know exactly how to solve it. Let's get started. The general form of a first-order linear differential equation looks like this. The first-order derivative dy dx, right up here, and the dependent variable y, right here, are both on the left-hand side. The differential equation is called linear because both dy dx and y are raised to the first power. A function involving the independent variable x is over here on the right-hand side, and then the coefficients a1 of x and a0 of x can be a constant or a function of x. A linear first-order differential equation is solved using what's called an integrating factor, and I'll tell you all about this in a few minutes. Before we look at the standard form, I want to make a quick note, and I want to point out that a linear equation can be a separable equation. And if it is, it should be solved using the method of separation of variables. I have a video on that method if you need to review that. Let's now talk about standard form. When you go to solve a first-order linear differential equation, the first thing you're going to do is put that equation in standard form. To put this equation in standard form, all you need to do is divide each term in the equation by the coefficient that multiplies the derivative. We take each term and just divide by a1 of x. Now the equation is in standard form, and we've renamed our coefficients. So the coefficient that multiplies y is p of x. It's just a0 over a1. And then the function on the right-hand side is just called q of x. To make things easier, I've written down steps that you can follow for solving any first-order linear differential equation. We're going to quickly go over all of these steps so that you can understand the theory behind solving these types of equations. Let's look at the first step. The first step is to put the equation in standard form. Since we just went over this, we're going to go ahead and jump to step 2. Step 2 is where you find the integrating factor. The integrating factor is called mu of x, and it's just e raised to the integral of p of x dx. P of x is just the coefficient right up here that multiplies y. You don't really need to memorize this formula. You just have to remember that the integrating factor is e raised to the integral of the coefficient that multiplies y. Now let's look at our third step. What you're going to do in this step is you are going to multiply every term in the equation, that's our equation here in standard form, by the integrating factor, and then you're going to simplify. We multiply each term by this integrating factor. When you're solving an actual problem, this integrating factor is just a function because you do the integration ahead of time. Then to simplify, notice that the left-hand side is the derivative with respect to x of the integrating factor times y. So what's inside this parenthesis is just mu of x times y. And then the right-hand side is the same. For the next step, you are going to integrate each side and then add on an arbitrary constant. We integrate the left-hand side and the right-hand side. Notice on the left-hand side that you're taking the integral of a derivative, so what you get back is just the integrating factor times y. And then your right-hand side is just your integral plus your arbitrary constant. In step 5, you just solve for y. Y is right here. I've written down what that looks like right down here. And then sometimes you will have a step 6. If you have an initial value problem, you'll have a step 6. And in this step, you just solve for the arbitrary constant. Let's now look at some examples. We're going to look at some examples where we are going to solve a first-order linear differential equation or initial value problem. On the left, I've written down the 6 steps that we can follow, and then on the right, I've written down the standard form of a linear first-order differential equation and its integrating factor. Let's look at our first example. The first thing that we want to do to solve this linear first-order differential equation is to put it in standard form. Standard form is where you just have the derivative by itself. This equation is already in standard form, so we'll just put done for this step. For step 2, we need to find the integrating factor. The integrating factor is mu of x, and it is e to the integral of p of x dx. P of x is just the coefficient that multiplies y. So in this case, it's -2. So we have e to the integral minus 2 dx. This is e to the minus 2x. You don't need to add a constant when you find the integrating factor because in step 3, we are going to multiply each term by the integrating factor, so the constant would just cancel out. Let's now multiply by the integrating factor. We're going to take our integrating factor and multiply every term in our equation by this factor. So we have a minus 2e to the minus 2x times y. And then on the right, we have an e to the minus 2x times e to the 2x. And those will cancel out. Now we need to simplify. What we end up on the left-hand side is the derivative with respect to x of e to the minus 2x times y. Our left-hand side is just the first term, e to the minus 2x, times the derivative of the second, using the product rule, plus the derivative of the first term times the second term. It always works out that the left-hand side is the derivative of the integrating factor times y. And then on the right-hand side, we can simplify and we get 1. For step 4, what we need to do now is integrate each side and add on our arbitrary constant. We have the integral of the derivative with respect to x, e to the minus 2x times y dx. And on the right-hand side, we have the integral of 1 times dx. On the left-hand side, we're taking the integral of a derivative, so we get back what's inside, and that is e to the minus 2x times y. And then on the right-hand side, the integral of 1 is just x, and here's where we add on our arbitrary constant. For step 5, what we need to do is just solve for y. There's our y. Let's divide by e to the minus 2x. This gives us y is equal to x plus c, all divided by e to the minus 2x. The best way to write this solution is to rewrite 1 over e to the minus 2x as e to the 2x. So our final solution is y is equal to x plus c times e to the 2x. And that's our final answer. Let's look at our second example. This example is more complicated than our first example because our coefficients are now functions of x and not constants. The first thing that we want to do is to put this equation in standard form. To do that, we need to get the derivative dy dx all by itself. So we're going to divide by x. This gives us dy dx plus 2x squared divided by x times y. And on the right-hand side, we have 2x squared divided by x. Let's simplify this. We have dy dx plus 2x times y. And on the right-hand side, we have 2x. For our second step, we want to find the integrating factor. Let's write down our formula. Our integrating factor mu of x is e to the integral p of x dx. P of x is just the coefficient that multiplies y. Let's go ahead and plug this in. This is e to the integral 2x dx. And this gives us e to the x squared. For our third step, we are going to take this integrating factor right here, and we're going to multiply every term in this equation by that factor. This gives us e to the x squared times dy dx plus 2x e to the x squared times y. And then on the right-hand side, we have 2x e to the x squared. Now we need to simplify this left-hand side. We're going to write the left-hand side as the derivative with respect to x of e to the x squared times y. That is just our integrating factor times y. And then our right-hand side stays the same, 2x e to the x squared. In step 4, we are going to integrate each side and add on an arbitrary constant. We have the integral d dx of e to the x squared times y dx. And then we have the integral of 2x e to the x squared times dx. On the left-hand side, we have an integral of a derivative, so we get back e to the x squared times y. And then on the right-hand side, we're going to have to work a little bit. To integrate the right-hand side, we are going to have to use u substitution. We're going to let u be x squared because we have the derivative of u already in our integral. Du is 2x dx. So notice that we have 2x dx right in our integral. This then becomes the integral of e to the u du. That's just e to the u plus c, and then we substitute back in that u is x squared. So we have e to the x squared plus c. Let's go ahead and put that in. On our left-hand side, we have e to the x squared times y. And now on our right-hand side, we have e to the x squared plus c. In step 5, we are going to solve for y. Let's go ahead and let's highlight that. It's right there. Let's divide both sides of the equation by e to the x squared, and that gives us y is equal to 1 plus c divided by e to the x squared. In this problem, we have one more step to do. Let's go back up to the top and look. We were given what's called an initial condition that y of 0 is equal to 2. When you're given an initial condition, instead of having a general solution like this, we're going to get what's called a particular solution. Let's write down our initial condition that y of 0 is equal to 2, and we want to find c from that. This just tells us that when x is equal to 0, y is equal to 2. So back up in the equation in step 5, we are going to substitute in that y is 2 and x is 0. On the left, we get 2, and then on the right, we get 1 plus c, that's what we're trying to find, over e to the x squared, so that's e to the 0. So this is just 2 is equal to 1 plus c, and we can see easily that c is equal to 1. Now we're going to take this solution and plug it back up into our equation for y. So our final particular solution is y is equal to 1 plus 1 over e to the x squared, and we can write that in a little bit better form by changing our exponential function, and we get y is equal to 1 plus e to the minus x squared. And that's the solution to our differential equation. Don't forget that you can always check your solution by plugging it back into your equation. That's just a nice built-in check with differential equations. Let's now look at our last example. I wanted to include this example because in this example, when we go to do our integration, we have to use integration by parts. Our first step is to put our equation in standard form. We want to get our dy dx all by itself. To do this, we are going to divide each term in our equation by x. This gives us dy dx plus 2 divided by x times y. And then on our right-hand side, we have sine x divided by x. Now we can go on to the next step, which is to find our integrating factor. That integrating factor is mu of x, and it's e to the integral p of x dx. P of x is just the coefficient that multiplies y. Let's plug that in. We have e to the integral 2 divided by x dx. That is equal to e to the 2 times natural log absolute value of x. We can pull the 2 up into the natural log. Just remember that a ln b is equal to the natural log of b raised to the a. That's why we can do that. So this becomes e to the natural log absolute value x squared. E to the ln of a function is just that function. So we get absolute value of x squared, but because it's squared, we can drop the absolute value and we just get x squared. Let me highlight this because that is our integrating factor. In our next step, we are going to go back to this equation right here, and we are going to multiply every term in that equation by our integrating factor. This gives us x squared times dy dx plus 2 divided by x times x squared times y. And then on our right-hand side, we have x squared times sine x over x. Let's go ahead and simplify this. We have x squared dy dx. This next term, one of the x's cancels, so we just have 2xy. And then on the right-hand side, our x in the denominator cancels, and we're left with an x times sine x. Now we have to do one more thing before going on to the next step. We need to simplify this left-hand side. This left-hand side is the derivative with respect to x of x squared times y. Notice that that's the derivative of the integrating factor times y. It's always going to work out that way. And then on the right-hand side, we just have our x sine x. Now in step 4, we can integrate both sides of the equation. That's going to enable us to eventually find y. We have the integral d dx of x squared times y dx. And then on our right-hand side, we have the integral x sine x dx. Let's work on our left-hand side first. We're taking the integral of a derivative, so we just get back x squared times y. And then on the right-hand side, we're going to have to do a little bit more work. We are going to have to use integration by parts. You probably learned that in Calc 2. Let me just remind you of the formula. When you use integration by parts, the formula is the integral of u dv is equal to uv minus the integral v times du. You always want to choose the u to be the function that when you take the derivative, it becomes simplified. We're going to let u be equal to x because when we take the derivative, we just get dx. And then dv is sine x dx. And we need v, so let's compute that. It's the integral of sine x, which is minus cosine x. So this integral is u times v, which is minus x cosine x, minus the integral of v du. So that's minus cosine x dx. This becomes minus x cosine x. And then we have plus the integral of cosine. The integral of cosine is sine. So we have a plus sine x. And then we're going to add on our plus c. Let's go ahead and rewrite this. On the left, we have x squared times y. And then on the right, we have a minus x cosine x plus sine x plus c. Let's now go on to step 5. That's actually going to be our last step because we don't have an initial value problem. We just have a differential equation. Step 5 is that we solve for y. We're going to do that by dividing by x squared. So we have y is equal to minus x cosine x all divided by x squared plus sine x all divided by x squared. And then we can't forget to divide our c also by x squared. It looks like we can simplify this first term. So let's do that. And we end up with y is equal to minus cosine x all divided by x plus sine x divided by x squared plus our c divided by x squared. And that's the solution to our differential equation. And that's it. You now know how to solve first-order linear differential equations by writing the equation in standard form, finding the integrating factor, and completing the integration process to solve for the dependent variable. Now you're all set to work some practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.